Welcome to this explainer. Today, we're tackling a seriously high-stakes engineering challenge. We're looking at how to stop an invisible, highly penetrating, armor-piercing threat. Yep, we're talking about neutron radiation. It's an absolutely fascinating problem because, well, neutrons don't carry an electric charge. And what that means is they can easily slice right through a lot of materials that would normally stop other types of radiation dead in their tracks.
So, you might be wondering, how do you actually build a wall against something like that? Now, neutrons are incredibly dangerous to human health, for sure, but they're also absolutely essential for modern life. We use them all the time for medical diagnostics, cutting-edge non-destructive industrial testing, and, of course, nuclear power generation. In the old days, our solution to shielding against them was basically just brute force. We're talking massive, incredibly thick concrete walls. And while the water and calcium oxide in concrete do a decent job, those walls are ridiculously heavy and completely immobile. That severely limits modern, compact applications. We literally need something better, lighter, and much smarter.
Okay, let's dive right into this. Here is our agenda for today. The neutron shielding problem, simulating with Fluka, match material to energy, building the ultimate shield, and finally stopping secondary gamma rays.
Section 1. The virtual testing ground. Simulating with Fluka. So to find an alternative to those giant concrete blocks, we can't exactly just blindly test materials in a lab, right? It's way too dangerous and incredibly expensive. Instead, researchers turn to the ultimate virtual crash testing ground for nuclear physics. It's a Monte Carlo simulation program called Fluka.
What researchers developed here is a brilliant, highly systematic methodology. First up, engineers use what's called a material card in the software to mathematically define the exact properties of different substances, like polymers or rare earth metals. Step 2, they use the beam pause card to fire a highly specific virtual beam of neutrons right at the material. Step 3 involves the USRB DEX card, and this carefully measures the radiation intensity right before it hits the shield and then right after it passes through. And finally, step 4, and honestly, this is my absolute favorite part. To stop the simulation from just running forever, Fluka literally uses a virtual black hole. Once a virtual neutron passes the shield and enters this black hole environment, it gets completely swallowed up, and the program happily terminates.
Now, just before we look at the results of these virtual crash tests, we really need to understand one vital term: macroscopic cross-section. To put it simply, this is the probability of interaction between a material and the neutrons passing through a given volume. Think of it like this. If you have a larger macroscopic cross-section, you have a much higher chance of actually stopping the neutron. Basically, a larger number means you've got better shielding.
Section 2. The heavyweights versus the sponges. Matching material to energy. Here is the core science challenge that researchers face. You see, neutron rays aren't all exactly the same. They come at vastly different energy levels, ranging from low-energy thermal and slow neutrons all the way up to highly energetic fast neutrons. And what these Fluka simulations reveal is that absolutely no single material can stop all of them effectively.
Which brings us to a really fascinating showdown between two completely different types of materials. We've got polymers versus rare earth oxides. Think of polymers, stuff like polyethylene and polypropylene, as a giant ball pit. Because they're packed full of lightweight hydrogen atoms, they are absolutely incredible at absorbing the impact of fast-moving objects through a process called elastic scattering. They essentially slow the fast neutrons down. On the flip side, rare earth oxides, like samarium oxide and gadolinium oxide, well, they act more like heavy sponges. They have massive macroscopic cross-sections for slow-moving objects, easily capturing and absorbing those low-energy neutrons through a process called radiative capture.
So, when we compare common polymers, polyethylene, or PE, is the clear winner here. And that's specifically because it boasts a massive 13.429% hydrogen content per unit volume. This super dense packing of hydrogen atoms totally maximizes elastic scattering. It makes PE the absolute ultimate moderator to strip the energy away from fast neutrons. But a pretty fascinating shift happens when we look at the low energy spectrum, those thermal and slow neutrons. The simulations show that our ball pit polymers actually lose their edge here. Instead, the rare earth oxides take over. Samarium oxide, seen here as SM203, shows an incredibly high macroscopic cross-section at these lower energies. It steps right in as the ultimate sponge to absorb what the polymers just can't handle.
Section 3. Building the ultimate shield. Tackling Californium-252. Okay, let's see how this all builds into a practical application.
We know polymers beat fast neutrons and rare earths beat slow ones. So what happens when we face a real-world threat that blasts out incredibly fast neutrons? Let me introduce you to the californium-252 neutron source. This isotope is widely used in industrial radiography and medical diagnostics, and it spits out highly energetic 214 keV fast neutrons. To shield against this monster, engineers really have to combine their best materials.
Researchers tested taking polyethylene, our ball pit, and samarium oxide, our sponge, and combining them into a thin 2-centimeter shield. But as it turns out, the structure totally matters. A stacked structure, where the materials are layered one after the exact other, achieves a shielding rate of 34.489%. This actually outperforms simply mixing the materials together into a uniform composite, which only achieved 33.692%.
Section 4. Stopping secondary gamma rays. So the really crucial point here is, why does stacking work better? Why not just mix them all up and call it a day? Well, the answer lies in a hidden danger that actually occurs during the shielding process itself: secondary gamma rays. See, when materials like samarium oxide absorb a neutron, the nuclear reaction actually spits out a highly radioactive gamma ray.
That's why the stacked composite is literally the ultimate engineering hack. It controls the sequence of events. When the californium-252 radiation hits the shield, layer 1, the polyethylene, takes the hit first. It moderates and slows down those fast neutrons through elastic scattering. And crucially, this process produces no secondary gamma rays whatsoever. Then, those newly slowed neutrons hit layer 2, the samarium oxide. Because the neutrons are already moving slowly, the samarium oxide can easily capture them. Now, while this capture does produce some gamma rays, there are far fewer of them, and importantly, they're being generated much deeper inside the shield, farther away from the surface. That makes it way safer for everyone around. If you just mix the materials together, you'd be blasting dangerous secondary gamma rays right out at the surface. It turns out, sequencing is absolutely everything.
Armed with this sequential logic, the researchers decided to scale things up. By taking that optimal, intelligently stacked composite of polyethylene and samarium oxide and increasing its thickness from 2 centimeters to 12 centimeters, they achieved a massive 92.885% shielding rate against the californium-252 source. I mean, that is an incredibly robust, lightweight, and efficient shield, and it was all achieved just by understanding the physics of the materials and the exact order in which they're arranged.
It is honestly amazing how much power there is in structured material engineering. By using virtual environments like Fluka, we don't just find out what works, we discover how it works best together. Which leaves us with a pretty fascinating thought. What other complex, invisible threats in our world could be totally neutralized, not by discovering some magical new element, but by simply rethinking how we sequence and stack the everyday materials we already have? Thank you so much for joining me for this explainer, and hey, keep questioning the structures around you.